Students, welcome to the lab of numerical methods CSE330. My name is Mahi Zakir and I'll be walking you through today's lab on numerical differentiation. To start with, I'll be talking about differentiation. So I'm assuming that all of us are already familiar with differentiation from our high school calculus courses. So during that period of time, usually we were given an equation that is assume we can assume that that's an quadratic equation like x squared plus 2x. So what we used to do is we used to get that equation that is a function, put put that in this function in this derivative function and produce a derivative which was another equation. So we used to get one equation from another equation using this formula, and this formula used to give us the exact and actual derivative at that point. So we can say that differentiation is the rate of change of a function with respect to the change in its argument, and the actual and the exact value is can be calculated using this formula. So moving on, sometimes that is in this course we will not be usually given the equation, like we won't be having the equation. So how can we calculate the differentiation of a curve without knowing its equation? Luckily, there is another way, that is using the concept of gradients. So to understand a little bit more about that, we need to talk about gradient. So what is gradient? Gradient is basically the change in y divided by the change in x. So if we have 2 points that are the y coordinates and the x coordinates, we can calculate the gradient of a point. So we also know that the differentiation at a point gives us the gradient at the same point. Um, During our maths courses, when we were asked to calculate the gradient of a curve, we usually did that by finding the derivative of the given equation and later putting on the x value onto the equation. So from there, I can say that the derivative of an equation can also be found by calculating its gradient. So, and gradient is also calculated by putting on discrete values such as the values of x and y. So from there we can say that the derivative is actually equal to this value. Not really actual but more approximate, because we are considering two different points of coordinates in here, and a graph can really move in a thousand or infinite number of ways between 2 points. For example, here we can see that the 2 points that we have considered are a straight line, because of course during calculating gradient during using two different points we assume that it passes as a straight line. However, the actual curve lies below the straight line and goes under, which means that the gradient that we are calculating will be slightly approximately equal to the actual gradient, but will of course not be the actual gradient. So summing up the concept of gradient and differentiation, we can say that gradient is the change in y divided by the change in x, and we find the change in y, we can find the values of y by putting in the corresponding values of x into the function, which will be polynomial for this course. We can also write the change in x-axis in, we can also replace the change in x-axis by a value of h. So the final equation is when we put in the two values of h, one is the first value of h and first value of x, and the second value we get that by adding an a particular step. Usually this value of step, that is the h value, lies between 0 to 1. It can be anything like 0 0.1, 0 0.2 or anything, but usually between 0 and 1, and when we add that constant number to the x, we get the second point of x, and we can get the corresponding y values just by putting it into the function. This way we get the gradient, and thus we can calculate an approximate derivative for our function. Once we understand what this formula actually means, we can say that there are different other ways in which this formula can be written. First, we can see that if we are at this point x and we move in a forward direction by adding a constant value of h to x to calculate the next coordinate, then the formula that we get is called the formula of forward differentiation, because we are moving in the forward direction. That is, if we have the value of x and we find the next value by adding a constant value to the corresponding x and thereby calculating and finding the values of y, we will say that this is the formula of forward direction. We can also do that by deducting the same amount of value, that is deducting h from x and move in the backward direction. That way we will also end up with two different points and we will also be able to calculate the gradient. But of course we have to keep in point that if we move in the backward direction, this will mean that the first point will be of higher value than the second point. So we will write f of x in the first position and then deduct the backward coordinate from this value, and of course deduct the whole value divided by h. Okay, so this is the forward formula that I have explained before, and this is the backward formula. There is another formula called the central difference. That is, when we do these derivatives by using both the forward point and the backward point. That is, we won't be working with the original x. We will instead be working with one step ahead of it and one step back of it. So if we take these two values and calculate the change in y by finding these two values, by deducting these two values, then the change of x-axis will be 2h, because there's one step and there's one step. The gap between these 2 points is 2h, so we will be deducting the whole thing by 2h. So this is called the central derivative formula. And these three formulas are very important because we will be seeing how to implement these formulas using Python and plot graphs using these formulas. Another thing that we need to keep in mind while calculating differentiation using the differences formula is that the central difference usually gives an lower error than using the forward and backward difference formula. This is mostly due to the part that it will be covering a larger area than the forward and backward difference. What I have said till now is mostly your theory content. Coming to the lab content, the things we need to know to complete this assignment and to plot numerical differentiation using the differences formula. Firstly, we need to be familiar with few libraries, then the polynomial module and few numpy functions, and we also need to know how to define various functions so that we can define the forward, central, and the other difference functions. Okay, moving on, we can divide the whole section of this whole content of this lab into three different parts, because while coding we will be doing three things. First of the first job that we need to do what we're asked to do is that we need to import the libraries. So what are the libraries that we need to import? First, we need to import NumPy as NP because we will be dealing with a lot of array lists, and we will, of course, also be doing few calculations. And there are a few other functions that are related to NumPy, and we will be using this. And those are the built-in functions of NumPy. So we will be importing the NumPy library, and from NumPy we will be importing the polynomial module, from which we will be from NumPy polynomial module we will be importing the polynomial class, because we will need to form polynomial objects, and polynomial objects are needed because it's much easier to work with this, because the equations that we will be given to find the derivatives of are usually polynomials, that is something to the power of x or something to the power of y. So we will be needing to import that, and lastly we will be importing the matplotlib.pyplot as plt, because we will need that to plot the graphs and see the error differences and the other legends and the graphs, basically the graphs. We will need this for the graphs. So to do this lab we need to keep in mind that importing these three libraries with their modules and every other thing is very important. So after importing, that is after writing these three lines in codes, we need to define the polynomial, that is the function of y. So how do we write polynomials? After we have imported this class, writing a polynomial object is very easy. We just write a variable name, give some variable name that is p1 for this case, and we write it as p1 is equals to polynomial, and we pass an array list into the polynomial object. So it is very easy to write this kind of equations because it's just putting on the list into the polynomial object. And what does this list means? This list is nothing but it's always in the same format. The first value means that it does not have any x coefficient. The second value means that it has an x coefficient but with power 1. The third value means that the x coefficient has power 2, and the fourth value means that x coefficient and power 3, and so on. So this polynomial is equals to this line because the 1 will represent 1, and so on. As I've said before, that the power of x's increases as we move on into the move on deep into the list. So it's very easy to write polynomials like this, and thus we will be using these polynomial objects to write our equations, the functions of which we will be calculating the derivatives of. So after writing the function, what do we need to find the derivative? If we want to use the gradient formula, that is the forward difference, central difference, and backward difference, we will need to know the corresponding values of y for the given value of x. So for example, if I say that we will be using two values and the given value of x is 2, we need to calculate the given value of y, and that will be, and how can we do that in code? It's very easy because we will just be using the variable name of the polynomial where we have stored the equation and just passing on x in a first bracket, and that will return us the value of y, corresponding y. Another thing that we can also pass to get the corresponding values of y is an array. We can also pass an array if we want to know more than one value of y. So if we want to know, like for example, the corresponding value of y when x equals to 5, 8, and 3, we can just pass these three values into a numpy array, name it as x, and then pass x into the original polynomial. This will return the array which will contain the corresponding y values. This is nothing but writing this line three times. So instead of writing this line three times, we can just pass an array and get an array in return. Okay, so apart from these two, we will also be getting familiar with the linspace function, which is also another way of linearly spacing the values of x, that is passing values of x so that we can calculate the corresponding values of y. And these values of x and y are very important since we are working with discrete values and not manipulating a function. Okay, so the first thing that we needed to know was the importing libraries. Second thing was how we will be declaring polynomials and how we will be getting the values of x. And the third thing that we need to know are few functions that will be very important to do the lab. So these functions are usually p1 p1 money. These functions are usually when we want to know the calculate the roots or derivatives or any other form of functions. Okay, so if we want to know the roots, that is when the function crosses the x-axis, I'm sure that we know what roots really mean. It is the function when the value of y is equals to 0 and we get the corresponding values of x. That is, the function cuts the x-axis. So we can get that value just by calling the roots function on the polynomial, and p1 is our polynomial which we have declared before. Okay, so and another function is we can also use the first formula that I had told you about, that we saw, that this generic formula of differentiation, this formula is built in into the numpy library, and we can use that just by calling the derived function on the polynomial. So this thing is very important to calculate the actual value, to know the actual value of the given derivative. We can call the derived function on the polynomial and get the actual value, and we will need this to compare that how much error is given when we have calculated it using the difference method and we from the actual value. And the last thing that we need to know is that the linspace function, this is nothing but when we when we want to pass several values of x and we want them linearly spaced, like this means that the values of x will be from minus 2.4 to 1.5 and they will be equally spaced, and there will be 50 values of x. By default the value of n is 100, but for this case I am mentioning that I want 50 values of x in between this. So if I call this function linspace and say that the domain of x will be from minus 2.4 to 1.5, it will just divide it and return me the values of corresponding values of y for those 50 values of x. This means that if I call this linspace function on the polynomial, it will be returning me two arrays. One array will contain the 50 values of x that will lie from minus 2.3 to 1.5 and one minus 2.4 to 1.5, and the other array will contain the values, the corresponding values of y when we put those values of x into the polynomial function. So we can, if we get the x and corresponding x and y values, we can easily plot them and get the curve, the actual curve that we are manipulating. So summarizing what we have learned till now, first we need to import these libraries as I have mentioned before, and after importing we need to initialize our polynomial. So we can do that by creating a polynomial object. P1 equals to, the polynomial is, P is capitalized letter polynomial, and what do? We pass an array list as the variables of the different coefficients, and we want to see what this equation looks like, so I'll be displaying this equation. And what else do we want? We will also be seeing its actual derivative, P1 actual derivative, and derivative. So the P1 actual derivative, how can we get that? We can easily get that by calling the P1 deriv function, which will give us the actual derivative equation, and we will also be displaying this P1 underscore actual derivative equation. Okay, so if we run this, we will see that these are the two equations. First equation is the function and the second equation is the derivative of the corresponding function. The other things that we also learned, that we can calculate that we can get the corresponding values of y just by passing on the value of x. So for P11 we will get the corresponding value of y, and if you pass an array, that np dot array, if we pass an array, we will get the corresponding value of array, corresponding values of y in an array. So what we do is pass the corresponding x into the equation and we will display this. No, we do not really need to display this. See, after running the code, we found the corresponding values of y in an array. And if we want to plot this, before plotting, we also need to learn about the linspace function. So the linspace function, what the linspace function does is, first thing that it needs to do is set its domain, that is the limit between which the values of x are allowed to function. So not function, sorry, fluctuate. So we can say that it can move from minus 1.4 to 2.6. So what I have said before, that if we set the value of n, then that the value of x will be linearly spaced in between this range 50 times. That is, we will get 50 values of x. So what this thing does is it creates it creates 50 points of x in the range of minus 1.4 to 2.6. So if we want the corresponding values of x as well for the corresponding 50 values of x, what we will do is we will simply give the we will simply write this thing in reference of the polynomial. This way, after calculating the corresponding x values, it will be sent into the function p1 polynomial so that it can give us the corresponding y values, and we can store it in, uh, let's say a variable called data. Okay, so what I've told before, if we do this, then the output that we get are two different arrays. The first array, that is data 01, data 0 contains the values of the 50 values of x, and the second array, that is data 1, contains the 50 values of y. So we can actually plot them, or we can actually display them as well. Let's see the 50 values of x. See, the data 0 contains the 50 values of x. If I write data 1 with it as well, we will also see the other 50 values, that are the corresponding values of 1, the corresponding values of y. Okay, so this is not really needed for now. So uh, so what else do we need to see? Okay, so we need to plot these things. So for plotting these functions, you do not really need to remember these functions, but you should be familiar with them because in the assignments, these are already given for you. So how do we plot? So for plotting, we have already plotted the matplotlib library, and we will be using the figure ax. The first figure, we will call it ax. We will call it ax, and of course it will be equal to plt dot subplots, because we want subplots as our figure space. So after defining that, what we need to do is we need to plot the data points, the data 0 and data 1 points. That is this. So if in the figure ax, if we plot data 0 and data 1 and want to label them as the function, because this is the main function, and we call the legend function so that we can see that the given function is fx. Okay, there is an error because I have forgot to include the first brackets after. Why is it not working? First brackets after the function. Okay, so we can see that with this we have got our function, and this is the actual function, the p1 function, because this is the actual function because we had sent the linspace, that the values of x into the main p1 function. We can also do this on the p-deriv function, the actual derivative function, and we will get the actual derivative equation as well. We will be doing that right now. Very same, it's actually the same thing. What we need to do is we need to copy this line. Okay, why is this thing not working? To copy this line, and it will be the same thing, just we need to pass the values of x into what? Into the actual derivative function polynomial. So we will be getting, and let's name this data d, because it will be the points of the polynomial, and we will be plotting these points in the same subplot. So we will be just changing the names so that it's easy for us to understand. Derivative. Okay, so if we run this function, we will see that the blue line is our actual function and the orange line is the actual derivative. Okay, so after working with the actual derivative functions, what we really need to do is we will be using this to calculate the errors. However, we need to write down the forward difference, backward difference, and central difference formulas. Those are very easy if we are already familiar. Moving on, after calculating the actual different derivative, actual values of the derivative, we need to use the forward difference and other difference methods to calculate the corresponding derivatives. To do that, we will need to define the forward difference function by ourselves, since we do not have a built-in function for that. And basically the main task is to build the forward function. So the forward difference function will be having three arguments as its parameters, because as we have seen in the equation before, it will need the equation of the function, it will need the value of h, and it will need a value of x. The x will be the starting value, and h will be the step difference between the second or previous values of h. Okay, so define this function, and for forward differentiation, we know that the derivative result that it will return will be by doing this calculation, which is it will first input the value of x plus h into the function and then deduct the value of f of x from the function. That is, it will calculate the change in y in this way, and after calculating the change in y, it will divide that whole thing by h. So this way it will get the okay, what is happening here? This way it will get the result, and after getting the result, it will easily return the result. Okay, so after returning the result, this is the way we have defined the function. We need to figure out how do we plot it. We plot it in the same way. First, we need a set of value of x, and we can say it, uh, save it in the variable xf, and we can use numpy and the linspace function to get our set of values of x. So our set of values of x started from 1.6, it will go till 2.4, and sorry, it started from 1.4, it had started from 2 point, and it will end at 2.6, and I want approximately 50 values in between. These are the values of x, and we need the corresponding values of y, which will be plotted, which will be acquired using the forward difference function. So we will call the function a forward difference function, and we will pass the corresponding equation which we have stored in the p1 variable, the polynomial, and the h value. Let's say the value of h for this is 0.5, and the x value. We have the x values in the xf variable. So this is it. So after calling the function, the corresponding values of yf will be stored in yf. So now we need to plot this, and we will plot this in the same axis ax, and we will pass xf and yf, and we will also want to label it as forward difference. Let's say it's forward. Let's just write forward, and we want to see the legend. So this is it. We run the code. Oh, and there it is. The orange color is the actual derivative, and the green color function is the forward derivative. We can see that the actual derivative, there is a little bit of error between the forward difference and the actual derivative, but it quite follows the pattern. So we can actually get an approximate value of the derivative from the forward difference function. The other things that we really need to know, that as we may change the value of h, that is the step difference between each value of x, the accuracy of the graph will be increased. So what is the value of h in here? We have passed the value of h as 0.5. Let's see what happens if we change the value of h to 0.1. See, the curve, actual curve, the actual derivative curve, and the forward curve, that is the orange curve and the green curve, are now overlapping. So we can see that the error is decreased in a substantial amount. Hence, we can say that in decreasing the value of h will give us higher accuracy and low errors. And we can also calculate the error at each point by deriving the actual value, from the value calculated using the forward, central, or backward difference formulas functions. Okay, so moving on, let's talk about the assignment right now. The assignment is very easy comparatively, because now with that we have an clear overview about the lab contents, we can easily go through the assignment. So the assignment starts with the three formulas. We are pretty much familiar with this by now. After that, as I have already said, that to start writing the numerical differentiation codes, we first need to import the specific libraries. So they have imported the specific libraries, and after that they have asked to define the functions. The forward function is already defined. The forward function, I have shown it a few seconds back actually. The forward function, I had stored this thing in result and then returned result, and they have done it in the same line. It's the same thing. So what you have to do for your lab assignment is that you have to write the backward difference formula in here and central difference formula in here, so that these three functions work. Okay, and after that there is a function called the error function, which will calculate the error for different values of h. As I've said before, that the higher the value of h, the greater the error. So we will start from a specific value of h and start and keep decreasing the value of h until the errors are of a low value. Okay, so the error calculation for the forward difference is already done for you. What is happening here? Forward difference using h value, h of a specific value of h. We use the specific value of h to call the forward function. So we get the corresponding value of y, and we deduct the y correct, that is the y actual derivative value from the return value of the forward difference function. And after getting the value, we get the f error for that specific h value, and then we add it to the all the other values of h, all the other values of errors for different values of h in an error in an array called the f error. It's called f error because it's for the forward difference. In the same way, you will need to write it for the backward method and central method. You will just need to tweak these two lines. That is, you will be changing just this thing will be backward difference, and this will be the same thing. The name will be b error h of I, and you will again have an b error array to which you will attend all the b error hi values. And the same way you will be able to do the central method. So the code is pretty easy for the assignment, and I'm sure that you guys can understand this. Okay, so that's pretty much your assignment. And the other thing, the plotting parts are already done for you. Please go through these codes, because this will give you a better overview of Python. And whenever you are going through the plotting code, you will see that you are already familiar with the codes. The I have used these codes while plotting the forward difference. I had used these functions before for during plotting the derivatives and the forward and the actual derivatives and the y coordinates and x coordinates using the forward and backward central difference formulas. So you're already familiar with these plotting things, and of course they have used the linspace function to generate the corresponding values of x and y. And p prime here is the p actual derivative. It stores the derivative function, actual derivative function, and they generate the corresponding x values and y values. So this is the same thing. I have already explained this code while writing the code, and so these are the written codes. Please go through them, because they are here so that you can actually run the code and see the corresponding answers. Here it's for the which one, it's for the forward, backward. Since the backward and central difference functions are not defined yet, these are showing error, but the all of this will show curves like this for different values of h when you finish this part of the code. Then all the other parts will be running smoothly. Okay, so this is it for numerical differentiation.